Chemistry time. Today we are talking about... Oh, speaking of that song, this is not a sponsor for the video. I think it is videoing. Can someone please confirm if this is videoing? This is a good joke. I love the way this is going. I was just about to... I told one of you students... Is it recording? Does it have a little number and it's going? Okay. Now is it doing a different thing? Now you're zoomed in. Good. Perfect. On my head. I was just telling one of the students that I've had this song stuck in my head all day, which is called "You Know My Name," and it's a song from a James Bond movie. And guess what today's topic is? Guess what the title's going to be? Nope. Nope. There you go. That's so cute. Isn't that a cute little joke? Bonds. And I can tell from the way that some students who will remain nameless because of the Federal Education Privacy Act said the word bonds like it was the stupidest thing they've ever heard. That apparently is not a very good joke, but I thought it was good. And it's just like a little miracle because I had the James Bond song stuck in my head. And we're talking about bonds. Well, whatever. Anyway, we're talking about bonds. The objective for this discussion and the objective for this video and the objective for our lesson, our lives at this time, is, read it aloud. I can't see it from here. Okay.
Types of chemical bonding.
Model and diagram. Types of chemical bonding. Bonds. Chemical bonds. Isn't that cute? Isn't that cute? Okay, that's enough of that joke. You guys are dead to me. When you know what's even worse than no one responding to your jokes at all is Ethan saying a student saying the syllable ha. Just exactly like that.
Wow.
Oh, wow. Okay, phew. At least you just said wow. What are the three main types of chemical bonds?
Physical.
Oh, and by the way, this should be review. We could even call this bonds, review bonds.
Ionic, physical, chemical, and ionic.
Okay, so one of those is right. Okay, let's start with that one. Covalent,
Valent.
ionic.
And valence. No.
Well, I bet it'll help you if I tell you that the covalent bond is usually structure. It's the force holding together, generally, a metal, a non-metal, and a non-metal. Or we could say two or more non-metals. Whereas ionic forms between ions, right? You would correctly say ions. You could specifically say a cation and an anion. But you might also say a metal and a non-metal. So, if covalent were a non-metal bonded to a non-metal, and ionic were a metal bonded to a non-metal, what do you think the last one is? Or let's start with this. What do you think it bonds? Metal bonded to a metal, and it's welding is a type of it. Or welding restructures these kind of bonds. Because we already said that, and it also wasn't it.
Is this a vocab word?
I mean, it's a couple of vocab words.
Monatomic ion.
No, it might not have been a vocab word. I think it should have been. I might have deleted it.
Ionic bond.
There's ionic bond.
Metallic bond.
You know what? I bet that's actually
I
it.
bet it's the metallic.
I bet it is the metallic bond. And to the extent that you're right, student, that you don't learn anything from your vocab, which I disagree with, to the extent that you're right, it's because you choose not to learn anything from your vocab. I don't think it's good that you don't learn from your vocab. I don't even think it's true that you don't learn from your vocab, but the fact that you think you don't learn from your vocab says a lot, which is bad. You have no right. Okay.
You just revealed his name. Yeah.
Student. Ethan's going to get DDoS. What do we, is that DOSed? Is that thing? I don't remember. Let's talk more about these. In a covalent bond, non-metals bind with other non-metals. We can pull this down now since Ethan's done with his test. And not only that, but the tests are graded. Bye-bye. Ethan's finally done with his test. Where would I find non-metals on this? Tell me this thing first. What's this guy's name? You know my name. Periodic table of the elements. Where would I find non-metals here, and what divides them from the metals? Yep, you got it. I'm going to draw a rough sketch of the periodic table of the elements here. Really extremely fat and rough. We've all got problems. Sketch of the periodic table here. It's actually not that rough. I've just improved it quite a lot by doing that. This little guy stair step line separates on this side of the stair step line. I actually still want to do that in red. Generally, these things are, can you see? Regarding the stair step line, these things are, here we are, metals. And these things are, I'm going to make it a little. Thank you. What I appreciate about this discussion is that we're all participating. Non-metals. Is that, well, this is as good a time as any, because part of, as I have chosen to do this as a review, one, you should know these already. That's the point of a review. And two, we're going to go through what are in your books, chapter 6, 7, and 8. Chapter 6 is about the periodic table. 6, 7, I don't know. Should I be saying that on YouTube? I don't know. We're about to find out because I'm going to look it up on Urban Dictionary, and then I'm going to take this video down, and I'm going to do other things. What's that? Yeah, sorry, Ami, you don't get to learn. I made a stupid decision with my words, and now you don't get to learn, Ami, a student. Chapter 6 is about the periodic table and the elements thereon. Chapter 7 is about ionic bonds, and Chapter 8 is about covalent bonds in general. And so we're trying to do all those at once, and so one thing we do need to talk about is, and you should remember, again, this is a review. Sorry, Ami, again, not for you, or maybe it is. I don't know what your life was like before you got here. But we should talk about what these individual things are, how the periodic table is arranged. In general, the periodic table is arranged how?
That's the atomic number.
Yes, by atomic number, by increasing atomic number. Good. And so if we look at these, what I'm diagramming here in blue, like Bluey. I don't know if you've heard of Bluey the dog.
I love Bluey.
Me too. We all love Bluey. But if you've ever heard of Bluey, you might recognize this color that I'm using. And this, we're diagramming the individual whats. What are these blues?
Columns.
Columns is an okay word. That's not what we call them on this periodic table.
What do you call them?
Great. That's why I'm asking you. Groups, or we also call them families. Because like a family, you might remember this little line, like a family, they have similarities in their properties, but they're not the same. If I look into this student's eyes, I can also, I'm not looking at you. Please don't look at me. If I look at this student's eyes, I can also see the eyes of his sister because they have similar properties. Do they have the exact same eyes? Do they share eyes? 2 eyes and 4 eye sockets like a monster, like a Halloween monster? No. Nope. You would notice if that were the truth, and it is not the truth. They do not have the same eyes, but they have similar eyes. And that's the same with these families on the periodic table. Similar properties, but not the same exact properties. You too have a sister who you do not share eyes with. You too have a sister. Multiple sisters. And you guys do not share eyes or hairs. Luke! Student! You too have a sister whose eyes you do not share, but they have similarities. Isn't that right? Ain't that neat? Don't talk about Ethan. Families have similar properties, but not the same. Let's name the families. I'm not going to say your last names, but you each have a name of your family, and you all share similar properties. Let's name these families. What's family 1 called?
1.
You know, he's not wrong, though. And in fact, most frequently, we do just call it group 1. But let's instead say a name, which you should remember.
I like
Eli just leaves. He's like, you know what? I've had it. Student, yeah, you're right. Yeah, you're right. Student is out. Student is like, I can't take this anymore. I'm just going to tell you, okay, I'm done with this. Group 1 are called the alkali metals. You should write this down. Alkali metals. Group 2 are called the alkaline earth metals.
Alkaline metal.
This is sometimes called group 3, but this is also sometimes called group 3, although usually we call this one group 13, which is what we're going to skip to. We will write that 3 through 12 are the transition metals, which is a vocab word, which you should have learned.
I knew that.
So that's these ones here. Good. 3 through 12. So then 13 is usually called group 13, correct? Sometimes called the aluminum group, and then very, very rare, well, I shouldn't say very, very rarely, but rarely called the icosagens. Group 14, nope. Why you say chemicals? Group 2 is alkaline earth metals. Yeah, I just got a little carried away with my penmanship. Group 14 are sometimes called the crystallogens. Group 15 are very often called the pnictogens. Group 16 are very often called the chalcogens. Group 17 are almost exclusively called the halogens. And then group 18 are almost exclusively called the noble gases.
Did you say 3 through 12?
Yep, 3 through 12. 3 through 12. 13, icosagens. 14, crystallogens. 15, pnictogens. 16, chalcogens. 17, halogens. 18, noble gases.
Can you read them and spell them?
No. And what makes these have similar properties? To carry on the analogy of the family, your DNA, maybe, your cellular expression is what makes you have similar eyes or hair or body structure to your family members. What makes these have similar properties?
Crystallogens?
That's not the right answer.
They all have similar properties.
Yes, they do all have similar properties. I'm asking you why.
Because they all have electrons.
They have similar.
You're getting close.
They all have the same valence.
They all have the same number of valence electrons. So looking at carbon, a crystallogen, and silicon, a crystallogen, do these two have the same number of electrons? No.
Yeah.
Carbon has how many? 6. And silicon has how many? 14. But how many valence electrons does carbon have? 4. And how many valence electrons does silicon have? 4. And so that's why they have similar but not the same properties. So alkali metals, how many valence electrons for alkali metals? 1. How many for alkaline earth metals?
2,
How many for transition metals?
3,
Usually 2.
usually
How many for icosagens?
3,
How many for crystallogens?
4,
Pnictogens?
5, 6, 7, 8.
How many now? Here's where we get into bonding. There are other things to talk about the periodic table. No, review bond. Here's where we get into bonding. How many do they want to have, in quotes? Most stable elements, except hydrogen and helium, are most stable with how many? 8 valence electrons. V is valence. With 8 valence electrons. What do we call this rule?
Organizers. No, it was like the octet rule.
The octet rule. And so these bonds, and this is why. Why bond? Why bond? Why does student want a girlfriend so bad, or boyfriend? It doesn't matter. Why does student want a girlfriend so bad? Why bond? To feel loved. That's a cute little answer. Why marriage?
To feel loved.
To feel loved. Why bond? To feel loved. Do you think that's the right answer here?
Yes.
Why do these atoms bond to feel alive? I mean, I'm not going to say it's not, but I don't think that's the physical reason why. Why bond?
To be more stable.
That's the answer for the physical, but I don't think that applies to my analogy. Like, man, I am unstable. I need a girlfriend. No. I think in general, this is starting to edge into philosophy or maybe even psychology, which I don't agree with psychology. I'll just say it. You can leave. The comments are not disabled for this video. You want to talk to me about how important psychology is, do it. I don't care. But I will say that in bonding in relationships, as well as in bonding in this, I think that the Venn diagram overlap area is that in both cases, there is something that the entity, an atom, a human, lacks that is made up for, that is fulfilled, we might even say, by another entity. Why bond? For these, it is to achieve stability. Now, to carry the analogy maybe one step too far, but at least one step further, just like there are some human beings that are living their best life, they don't need no man or woman, like they can live their best life independently. Some of them, noble gases, already have satisfied the octet rule on their own. Do you think noble gases bond? No. Yeah, rarely. Not never, but very rarely. Why bond? To achieve stability. These other ones bond in order to be more stable. And the type of bond they form depends on how many electrons they had to start out with. So covalent bonds are between a nonmetal and a nonmetal. Ionic bonds are between a metal and a nonmetal. And metallic bonds are between metals.
Like sodium chloride.
Excuse me. So let's do some examples of these, because the main thing that we do for this chapter is name and write formulas, which you should be familiar with from physical science. You have a lot of practice to do on it, but the main thing we do is write names and formulas is the main activity in this chapter. So let's talk about covalent bonds first. Covalent bonds can be unevenly or evenly shared. Unevenly shared we call polar. Can you guess what we call evenly shared? Nonpolar. And this has to do with how strongly each of the substances in the molecule, by the way, covalent bonds are sometimes also called molecular bonds, are shared. The classic example is if I have an oxygen. I'm going to draw the electron dot diagram for oxygen, which is usually depicted in red. How many valence electrons should I draw around the oxygen? 6. 1, 2, 3, 4, 5, 6. And let's say the oxygen is existing in an environment of hydrogen. So I've got some hydrogens floating around. I'm going to do those in a different color. I guess yellow because I want to make this as hard as possible for you to see. How many valence electrons should I draw around the hydrogen? Try again. 1. And again, if I have another hydrogen here, 1. By the way, except hydrogen, how many does this want? It's an exception to the octet rule. How many does it want? It wants 2. Both hydrogen and helium are more stable with 2. Is there a way that you think that these hydrogens and this oxygen could help a brother out?
Yes.
Yeah, how?
Covalent bond.
A covalent bond. They could share. Like if you cooperate, you're sharing the operation. They could covalently bond. Covalence, meaning their valence electrons. They could share their valence electrons. So the hydrogen could come over here. And the other hydrogen could come over here. Now they're sharing. Now, how many valence electrons, since they're sharing, does the oxygen have?
8.
It has 8. How many does the hydrogen have? And how many does the hydrogen have? Everyone's happy. So this is both more stable than either hydrogen or oxygen. And you can see that even though they're all sharing, where do the electrons want to hang out the most?
Next to each other.
No, not that. Just directly not that, because they all have the same charge, and so they want to get as far away from each other as they can. With whom do the electrons want to spend more of their time? No, with whom of these 3 guys, or ladies, I don't care, doesn't matter, guys, gender neutral. Why oxygen? You're right, but why? Yeah, because oxygen has the most protons, which attract electrons, right? For the opposite reason you said they want to hang with other electrons, they don't. They're repelled by other electrons. They want to hang out with protons, and oxygen has the most. And so this bond becomes unevenly shared. The electrons want to spend more time with this, and so we end up with a polar covalent bond. Polar covalent bond. There's a chart in your book on page, I'm already there, 265, that shows electronegativities. Depending on the difference, what mathematical operation is that? Subtraction. Depending on the difference in the bonds, the element's electronegativity in that bond, the bond nature will either be ionic, polar covalent, or nonpolar covalent. Now, let's do another example. Oh, BT dub, what do we name this? What's the name of this? That's not a name. You're right, it is H2O, water. There are naming rules that we will get to. This is an exception. If you call this dihydrogen monoxide, which would be following the rules, you're wrong. You will get it wrong. It's just called water. We always call it water. This is an exception. I started with an exception because I'm an idiot. But we will do the rules that aren't exceptions pretty quick. Now, what if instead, I wanted green. What if instead we have chlorine? How many valence electrons should I draw around her? 1, 2, 3, 4, 5, 6, 7. And what if I have chlorine? How many valence electrons should I draw around her? 1, 2, 3, 4, 5, 6, 7. Can you think of a way that these two could sort it out, make each other happy?
No. Yes.
You just can't. Refuse. I won't. How?
They combine the two.
Could they covalently bond? Could they share their valence electrons?
You can share.
How many valence electrons does the chlorine have? How many valence electrons does the chlorine have?
8.
They're both a little more stable. Now, if you're an electron, who do you want to hang out with more? Chlorine or chlorine?
Chlorine.
You're right. It doesn't matter. So this is going to be a non-polar bond. They're evenly shared. This is like both your cool divorced dad and your cool divorced mom both have an Xbox. You don't care. Just go wherever you want. That's not a good joke. I'm really sorry about that one. Sorry, Almy, for making all these jokes that are going to make my video struck off of YouTube. So these ones have shared their bonds. They're both non-metal, and so we say these are covalent bonds. And this specifically, this one is a non-polar because they're evenly shared. This one is yes polar because it is unevenly shared. Oh, I'm sorry, and I missed a really important part, which is that since the electrons want to hang out more with the oxygen, this end becomes partially negative, which we indicate with the lowercase delta negative, and this end becomes partially positive, which we indicate with the lowercase delta positive. So what? Good. Okay. Now, what if instead we have a metal? Give me an example of a metal. What's the matter? Did you throw up?
Iron.
How many valence electrons does iron have?
2.
Let's say it has 2. And although iron's not a great, we're going to use the iron. Iron's not a great example because it can also bond with its D shell electrons, and so it could have a charge of +2 or +3. But we're going to pretend in this case that we're just using its 2 valence electrons. Now let's say this iron is in a chlorine-rich environment again, and here comes a chlorine. And here comes another chlorine. It might seem like this chlorine could just covalently bond with the iron again, but actually the chlorine wants the electrons so bad, and the iron doesn't want them. Why? What's underneath here? If the iron gets rid of its 2 valence electrons, what's under there? Chaotic answer. What is underneath this layer of, if it gets rid of these 2 valence electrons, what's next down? Well, more electrons, and it happens to be a full shell. It's not actually 8 because it has d orbital electrons, but that's why it can bond with those 2. That's why I wish you didn't use iron, but it's okay. So the iron actually wants to get rid of these electrons. And this is the example I always use, and it's going to be especially applicable to you guys. Just like your parents desperately want you out of the house, but they have to make sure you're going to go somewhere safe, married, job, college, whatever. They can't just throw you out on the street. They can't, I mean, they could physically lift you and put you out on the street probably, but they don't want to do that. They want to make sure you're going to be safe. And so the electrons can't just go away. They have to go somewhere. Like when you read in the newspaper about to a good home, the person doesn't want to shoot their dog. They just want to get rid of their dog, and so it has to go to a good home. Same with electrons. The electrons have to go somewhere, and in this case, the chlorine. Now, tell me the formula for this. This is an ionic bond, by the way. Now that this iron has lost valence electrons, what's its charge going to be?
0.
Positive 2. What's the chlorine's charge going to be?
-1.
-1. What about this one? -1. And now, opposites attract. The chlorines, even though they have the electrons that they came for, they're still bound up in the iron because they are attracted magnetically. Tell me the formula for this compound.
Big hole.
That is not a formula. That's nothing. Tell me the formula for this compound.
FeCl.
2. What's this little 2 represent? This is review. There are 2 of them. It does not represent the charge. Let's try to say the right answers, okay, student? So think about the right answer and then say them.
We already know this thing.
So we only put how many there are. That's what this little baby 2 represents. The baby 2 represents how many there are. So if we want to name this, which we do, what would we name it? Well, what's its first name? Iron? You're not wrong, but there's something in between. It is iron 2 chloride. Very good job, student. Because this 2 in Roman numerals does indicate the charge. Because iron, as almost all of these can, you always have to do this with transition metals, can be either a 2 or a 3 charge, and so you have to say which one you're talking about. Because iron 2 chloride, FeCl2, and iron 3 chloride, Fe2Cl3, have completely different properties from each other. They are not the same substance. They're totally different, and so we use this symbology to indicate which one we're talking about. So we do that for ionic compounds. Another thing about ionic compounds is that what if we had sodium this time? I'll just tell you one so that you don't come up with another transition metal. Well, you know what? I don't even care. Give me a metal. We'll do it your way. Give me a metal.
Barium.
Let's not use gold. It's good. Barium's good. How many valence electrons should I put with barium? Okay. Sometimes covalently bonded groups of molecules can behave as an ion. Can you guess what we might call that ion? If we had an ion made of many atoms that are covalently bonded together, what might we call that one ion?
Ion.
What kind of ion?
Oh, polyatomic.
A polyatomic ion. Which brings me to my next thing. We have a polyatomic ion quiz
When?
right now.
Oh gosh.
So what if we have over here a little, oh, I'm going to do this in a different color. What if we have over here a little sulfur that is covalently bonded with 4 oxygens, and the whole thing has a -2 charge? It's a polyatomic ion. Which polyatomic